In this lecture, I want to talk about some properties of probability. That is, these are properties that every probability satisfies no matter what stochastic truth table you're working with. We're going to talk about the so-called probability axioms. So first of all, there are three key properties that every probability function satisfies regardless of the stochastic truth table you're working with. First of all, just built into the definition of a stochastic truth table is that every row must be assigned a number that's greater than or equal to 0. So that means when you look at the probability of a particular formula, which is going to be the sum of the probabilities assigned to each row, this number must be always greater than or equal to 0. Now, of course, it might be equal to 0 if all the rows in which phi is true happen to be assigned 0. So the probability of phi might be 0, but it always has to be at least 0. So it must be greater than or equal to 0. In addition, another property of a stochastic truth table is that the sum of the probabilities on every row must be equal to 1. So that means that if phi is a tautology, where a tautology means that phi is true on every row of the truth table, then the probability of phi must be equal to 1. These two things together basically give you that the probability that you assign to every formula must be between 0 and 1. One final property, and this is a crucial property, is that if phi and psi are mutually exclusive, that is, there's no truth value assignment that makes both phi and psi true at the same time, then the probability of phi or psi is going to be the sum of the probability of phi plus the probability of psi. And you can see that. Suppose that you have a truth table here. So say we'll just do one with P and Q. So this is true, 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 false, false, true, false, true, and false, false. And say you have some formulas phi and psi. Right? Now, we don't know what those formulas are, but they're arbitrary formulas. Now, every row, if this is a stochastic truth table, this is going to be assigned some number P1, this will be P2, that's P3, and that's P4. Now, let's say that phi and psi are never true on the same row. So let's say that phi is true only on row P1, so this is where phi is true. And let's say that psi is true only on rows 3 and 4. So psi is true here and here, but false everywhere else. Now, the probability of psi is going to be P3 plus P4, and the probability of phi is going to be P1. Now, what is the probability of phi or psi? Well, phi or psi is true on every row in which either phi is true or psi is true. Well, that's going to be rows 1, 3, and 4. So the probability of phi or psi is P1 plus P3 plus P4. And of course, those two numbers are in fact the same when you add up the probability of phi to the probability of psi. So just in a picture, if phi and psi are mutually exclusive, then when we draw the places where phi is true and the places where psi is true, these circles are not going to overlap. So this is the phi region and this is the psi region. So the probability of phi would be the probability of this region right here. The probability of psi is going to be that region. And then the sum of those two probabilities is, of course, going to be the probability of phi or psi. Now, using those facts, we can actually derive other properties of the probability function. So in particular, the probability of not phi must always be equal to 1 minus the probability of phi. Well, why is that? Well, phi and not phi are mutually exclusive. There's no truth value assignment that makes both phi and not phi true at the same time. So that tells me that the probability of phi or not phi is going to be equal to the probability of phi plus the probability of not phi. Furthermore, phi or not phi is a tautology, so I know that this probability must be equal to 1. So we get 1 is equal to the probability of phi plus the probability of not phi. So just pushing subtracting the probability of phi from both sides, we get 1 minus the probability of phi is equal to the probability of not phi. So this is a general rule. In any stochastic truth table for all formulas phi, the probability of not phi is always 1 minus the probability of phi. This immediately tells us that if phi is a contradiction, then the probability of phi must be equal to 0. Because if phi is a contradiction, then not phi is a tautology. And we know that the probability of not phi must be equal to 1 minus the probability of phi. But if not phi is a tautology, we know that this must be equal to 1. So if the probability of not phi is equal to 1, and the probability of not phi is equal to 1 minus the probability of phi, the only thing that the probability of phi could be is 0. Two other properties. The first one is that in all stochastic truth tables for all formulas phi and psi, if and only if psi is a tautology, that is, phi and psi are tautologically equivalent, then their probabilities have to be the same. This is relatively easy to see because the probability of phi is the sum of all the probabilities of the rows in which phi is true, and the probability of psi is the sum of the probabilities of the rows in which psi is true. But if phi and psi are true on exactly the same rows, then you're going to be adding up the same numbers. So if two formulas are tautologically equivalent, then they must be assigned the same probability. We can use this idea to derive this other really important fact about probabilities. Namely, the probability of phi must be equal to the probability of phi and psi plus the probability of phi and not psi. And this is easy to see once you note that phi, if and only if phi and psi or phi and not psi, is a tautology. So this tells me that the probability of phi must be equal to the probability of phi and psi or phi and not psi. But of course, phi and psi and phi and not psi are mutually exclusive, so this is equal to the probability of phi and psi plus the probability of phi and not psi. So in a picture, here we have phi, and now we have psi. We note that this region right here, the red region, is phi and not psi, whereas the blue region is phi and psi. So we see that, and they're disjoint, they don't overlap. So the probability of the phi region, this region right here, is going to be the sum of the probability of the red region plus the probability of the blue region. And that justifies this formula right here. Here's a general fact about disjunction. So remember, we said that if phi and psi were mutually exclusive, then the probability of phi or psi is the sum of the probability of phi plus the probability of psi. Well, what about if you just have two arbitrary formulas, phi and psi, that are not necessarily mutually exclusive? Well, let's draw, it's easier to see if we draw a picture here. So here we have phi, here we have the psi region. Now let's highlight the phi and not psi region. So this is phi and not psi. This region right here is going to be the psi and not phi region. And the region in the middle right there is, of course, the phi and psi region. So we can see directly that the probability of phi or psi is just going to be the sum of the probability of these three disjoint regions. So we have the probability of phi or psi is equal to the probability of phi and not psi, plus the probability of phi and psi, plus the probability of not phi and psi, or psi and not phi. Now, what about, so how do we get the right-hand side of this equation right here? Well, we use this previous fact about the probability of phi. And we see that the probability of phi is equal to the probability of phi and psi plus the probability of phi and not psi. The probability of psi is going to be equal to the probability of psi and phi plus the probability of psi and not phi. So if we were to add the probability of phi plus the probability of psi, we would get the probability of phi and psi plus the probability of phi and not psi plus the probability of psi and phi plus the probability of psi and not phi. Now, let's just see here. So here we have the probability of phi and not psi. So we have the probability of phi and not psi right here. We have the probability of psi and not phi. So this is the probability of psi and not phi. But in this sum right here, we added the probability of phi and psi twice. So, but up here, when we calculated the probability of phi or psi, we only added one probability of phi and psi. So in order to make these two sums equal, we need to subtract one of the probabilities of phi and psi. Because of course, the probability of phi and psi is equal to the probability of psi and phi. So we have to subtract off one of these. And that's where we get this formula right here. The probability of phi or psi is equal to the probability of phi plus the probability of psi minus the probability in which they overlap. What about this second property right here? Well, if phi implies psi is a tautology, then the probability of phi must be less than or equal to the probability of psi. Well, we can see that pretty quickly by drawing a picture. So here we have the psi region, and if phi implies psi is a tautology, then every place where phi is true must be contained in every place where psi is true. So phi is completely contained inside of the psi region. So the probability of this region, of course, must be less than or equal to the probability of this bigger region that contains it. A bit more formally, let's look at the probability of not phi or psi. Now remember, not phi or psi is logically equivalent to phi implies psi. These two formulas are tautologically equivalent, so the probability of these two formulas are the same. So this probability is going to be equal to 1. But using the equation at the top here in this first property, this is going to be equal to the probability of not phi plus the probability of psi minus the probability of not phi and psi. Now, the probability of not phi is going to be 1 minus the probability of phi plus the probability of psi minus the probability of not phi and psi. So we get 1 equals 1 minus the probability of phi plus the probability of psi minus the probability of not phi and psi. So if we were to simplify this equation a little bit, the 1's are going to cancel, and I can add the probability of phi to both sides. So I'll get the probability of phi is equal to the probability of psi minus the probability of not phi and psi. Now, we reason as follows. The probability of phi is some number between 0 and 1, and the probability of psi is some number between 0 and 1, and this probability is some number between 0 and 1. Well, this number has to be less than or equal to this number, because this number is equal to that number minus some positive value. So this value might be 0, so these two, probability of phi and psi, might be the same. But if this probability of not phi and psi is non-zero, then the probability of phi must be less than or equal to the probability of psi, because this is a positive number. So you're taking one number minus some other positive number, and you get this first number.